and the next keynote lecture will be given by Professor Anthony Peirce. So Professor Peirce, please.
Well, thanks very much for inviting me to your conference and giving me an opportunity to share some of the work with me, some of my work with you. I just want to acknowledge some of my collaborators, Andy Bunga, whose, Andy Bunga, whose experiments are amazing, Emmanuel de Tournay, who I've done a lot of work with, Yegor Donsov, who you just heard, and Lisa Godelli, and Ed Siebritz, who got me involved in this sort of modeling for a long time ago. So today I'm going to talk about the tip. And you'll see in a lot of Yegor's modeling, he actually did a lot of sort of averaging, but he was very careful to make sure that he got the tip right. And hopefully that's going to convince you, just by some fairly simple analysis of some of these basic equations, we'll be able to show how important the tip is. And I'm sort of going to quote here this word asymptotology, which is defined as the art of dealing with applied mathematical systems in limiting cases. And these limiting cases often end up being very challenging for numerics, but asymptotic analysis typically leads to a simplified system, which you can solve, sometimes with your bare hands. And the hydraulic fractures are no exception, and we'll see that I claim that the tip is the tail that wags the dog in terms of hydraulic fracturing. So don't be scared of the tip. The tip asymptotics can be very useful. Okay, so the sort of modeling I'm going to be talking about is continuum modeling. Basically, two types of models I'll be talking about briefly. Firstly, boundary integral models. We've seen a whole lot. Professor Linkoff spoke about that. Yegor spoke about that. Boundary integral models are great because you can reduce the dimension of everything by one. So you could have a fracture curve in a 2D elastic medium, or a planar fracture, for example, in a 3D medium. The problem is you need to assume linear elasticity. Inhomogeneous problems are difficult, but the positive side is you only discretize the boundary. Finite element methods, which are sort of the go-to methods for engineers, require sort of lots of remeshing. They can deal with nonlinear materials, which is good. And then there are the extended finite element models, which basically try to sort of make finite elements look a little bit like boundary elements, because essentially you only discretize the boundary of the crack and you enhance your basis functions to see the singular behavior of the crack. So I'm going to be talking about how the tip asymptotics can be built into these cracks and these cracks and these cracks, for example. Okay, so let's go to essentially what amounts to a boundary integral formulation. Oops, sorry, I've got a boundary integral formulation. This is the standard lubrication equation. Essentially, PF is the fluid pressure. This is the source of fluid that's assumed to be a point source. W is the fracture opening. And we have viscous fluid loss, viscous energy loss here. There's energy consumed breaking the rock. This is essentially how the fracture toughness affects the asymptotics. We'll see that later. And the fracture toughness and the energy, as Yegor was showing, is related by this relationship. And this is essentially, that's a statement of balance of mass within the fluid within the fracture. And this is a statement of equilibrium. So the forces on the boundary of the crack minus the geological stresses relate to the fracture opening through the elastic modulus. So this is a singular integral equation. And we have these boundary conditions. One of the big problems is it's a free boundary problem. So we don't know where the boundary is. So if we sort of took the L as a parameter, we could get multiple solutions to these with different L's. Okay, so there's a uncountable infinity of solutions, actually. And the important thing is to select the correct L appropriate for the particular situation. So that's actually one of the big challenges. If you discretize, you get this evolution equation, much like what Professor Linkoff was talking about, and you get this elasticity equation. Okay. So what I'm going to do now is to sort of do what one does typically in applied mathematics. You transform to a moving coordinate system. Think of ourselves as a flea on the tip of the crack, moving at the velocity v. And rather than use the global coordinates, we introduce a local coordinate x hat, which is L minus x. And we introduce new variables, w hat as a function of x hat, okay, which looks like this. And then you plug into the system of equations, and the lubrication equation, that time derivative introduces this convective term, and the lubrication equation ends up looking like this. Basically, everything is the same except for this term, and this has been shifted. And the integral now, instead of going from minus L to L, goes from 0 from the leading tip to the other tip. Okay, so what we now do is to zoom into the tip because we want to see what's going on there. So we zoom into the tip with the scaling, and this delta and this epsilon, these epsilon and delta factors are just sort of length scales that we're going to adjust and play around with. So we're thinking of delta as being small and x of order 1, big X of order 1, and similarly W. And we're going to adjust the sizes of these. So if you plug into the equations, apply the chain rule, you end up transforming everything to look like this, right? And if you balance, for example, this term and this term, okay, you actually end up with a viscous asymptote. And it shows that the width goes like this 2/3 power, and the pressure is singular with this minus 1/3 power. If you balance, for example, this term and this term, you end up with this 5/8 power, and the width goes with this 5/8, and the pressure is also singular. Okay, so another way to look at this is this is very analogous to what you learn in simple ordinary differential equations in terms of Frobenius series. You look for a power law solution, and go back. You look for a power law solution, x to the alpha, where alpha is a parameter. And it just so happens for the semi-infinite fracture, notice when we let delta go to 0, this L being finite, this thing goes from 0 to infinity. So we can think of this as we're zooming into the tip. We could think of this as being from 0, an analysis where this goes from 0 to infinity. So this power law happens actually to be an eigenfunction, because basically this is some simple complex analysis, this eigenfunction is reproduced. This integral operator reproduces this eigenfunction exactly, and this is the eigenvalue. So if we look at the lubrication equation with this power law, you can integrate it. And now if we look at, say, the K vertex, where we've got a x to the half power, then basically we can, if we're looking at these two terms cancelling or matching, then that W cancels with this one, and we get W squared. X to the half gives us basically x over here. dp dx means that the pressure is going to be has a log singularity. Now looking when alpha is not equal to a half, so alpha equals a half is a degenerate situation because it generates no stress in this situation. But when alpha is not a half, then these are the power laws that are associated with these terms. And if you match those two, lo and behold, you get the viscous asymptote. And if you match these two, pretty much like we did in the previous analysis, you get the leak-off asymptote. Okay, so just looking at how these power laws stack up, basically I'll just plot this here. So if you plot from 0 to 1, you know, as a x to the alpha, you'll see that basically the smallest power will always win, right? We all know this from elementary mathematics. But so the hierarchy of power laws is like this. However, we notice that the toughness is a constant throughout the propagation. However, here you have a velocity term here. So basically, as the fracture propagates, these terms can sort of the green and the red, the green and the blue, the leak-off and the viscosity asymptotes can beat the toughness asymptote as long as you're far enough away from the fracture. Ultimately, you'll get close enough that the red one, the x to the half, will win. So you can see, just from comparing these solutions, you can see the existence. We could see that there can be multiple multi-scale behavior that will occur on many different time scales and on many different length scales. So ultimately, these things can exchange order. You can have different combinations of them. Everything is possible. Ultimately, the pressure is singular in these with these sort of powers. So it's possible to do an analysis by solving these reduced equations that we got from the asymptotics. This was done by Dmitry Garagash, Emmanuel de Tonnay, and Adachi in 2011, and then Yegor Donsov and myself. We found a simpler way to do it. But basically, if you do a cross-section over here, you'll see that if you're close to the tip, you'll go from the toughness regime, which is in red, to the viscosity regime. So this is a section here, which is this white line. If you go a bit higher up in this diagram, okay, later in the process, or for a different set of parameters, if leak-off is present, for example, or becomes more dominant, then you'll see that essentially you can go from toughness to leak-off to viscosity. So you get a sort of triple deck of asymptotics, three different asymptotes, all in the same, active in the same hydraulic fracture. And the trajectory as you go away from the tip is from toughness to leak-off to viscosity. So as you traverse that. And here's a sort of plot of these different length scales. Everything scaled to the toughness asymptote, leak-off, and viscous. Challenges with the governing equations. So this is basically getting back to Professor Linkoff's talk. I have been sort of looking at solving these equations implicitly. I mean, what Professor Linkoff was talking about today was actually just doing the CW, doing this matrix multiply. If you do this evolution, you can keep just doing this matrix multiply. However, if you do implicit time stepping, you can also solve the equations by actually singling out the singular multiply and keeping that as its own entity. So you could use his fast multipole method if you just separate this out in the iterative procedure. The problems are that we have a singular pressure field, multi-scale tip asymptotics, and a singular free boundary problem. And you've got this distinguished limit that you have to calculate, 0, something that's going to 0 times something that's going to infinity. So those are the challenges. So how do you deal with this? How do you capture the free boundary? Okay, so I'm just going to briefly outline this implicit level set algorithm that Professor Linkoff mentioned this morning. And the idea is fairly simple. You use the tip asymptotics to find where the fracture tip is. So assume that you have a sort of guess for where the fracture is. Okay, and W is the fracture opening. Then say we were on the toughness asymptote, we would know that W is K prime E prime S to the half. And inverting this relation, you end up with S being given, if you knew W, you would know what S is. So basically you assume, you take a guess for the fracture position, you calculate from those two equilibrium equations what the width and pressures are, and then you determine a new guess for S. Okay, in the viscous asymptote, the same thing, you can invert this relation. Now you think, oh, well, we're fooling ourselves because we need the velocity, but basically you can plug in this finite difference approximation for the velocity and you get a little cubic. So given W, you can find what S is. So that's essentially what's going on. So you set the tip widths. If you knew what W was, you know where the tip is. Given the tip, what you can do is you can set the tip average value to be the fracture opening in the tip to be the average value for that asymptote. Okay, and now all you do is you specify that the volume of fluid flowing in to the, V old is the previous fracture opening times delta X, and this is the new fracture opening, and that must match the amount of fluid that flows in. Okay, so that would have the expression, if you use the lubrication equation of this is conservation of mass. And basically the tip is known given the, whoops, I'm having finger trouble here. The tip is known given where the free boundary is. The tip width is known. So the pressure in the tip becomes a primary unknown. So you have this mixed sort of problem. So now how does that translate into sort of asymptotics for a hydraulic fracture with multi-scale behavior? Well, we could just take Jaeger's plot there, and basically we map this piece of the tip onto this region in this dimensionless space, or this X space, and basically you integrate all of this, and so you're including all this multi-scale tip asymptotics, but in what we call a weak sense. Okay, so it's possible to capture multi-scale behavior in a very coarse, on a very coarse mesh. Okay, so here you could even get toughness, leak-off, and viscosity, all included in that multi-scale behavior. Okay, so here's a sort of little animation. You get a trial width. You determine where the free boundary is. You set the average widths. You update the fracture width again. Look where the free boundary changes to. Now you update the average widths, and you iterate. And if you have a look, I'm comparing it to the exact solution, which is the red. Even though you're using a very coarse mesh, we're actually doing a fairly good job. Okay, so I'm not going to talk much more about that. You can extend this to the extended finite element method. Basically, you introduce these step function, basis functions, and you enhance the tip with the appropriate power law that you want, and these are the sort of enhanced basis functions. And I'm just going to show you some results. This was work with Lisa Gordelli. This was a fracture near a free surface, and it's sort of curving, and we managed to match a boundary integral code. And here's an animation of that process. So it's possible to build all that multi-scale behavior into a finite element context with the extended finite element method. For planar fractures, I'm just going to briefly talk about this. The same principle holds. We've also got this horrible free boundary. If you zoom into the tip, if you consider yourself an ant that moves really close to the free boundary, this starts to look like an infinite wall, and basically the two-dimensional operator, the planar operator, is reduced to the plane strain operator. So everything that we've done for the plane strain case now applies, and now we can do the same old process. So here,
5 minutes left.
Okay, thank you. I'll good. Thank you very much. So here we with some trial widths, we can determine where the free boundary is, and knowing where the distance to the free boundary is, we can solve this level set, this iconal equation, and determine exactly where the free boundary is. So this is just sort of more details. Here's the level set function, if you like, level set surface. You can build in multi-scale asymptotics. So this is all possible and published. So here are just some animations. This is a comparison with an experiment in the viscous regime. You can see the black line is the numerical, the gray line is the experiment. If you put M and K, toughness and viscosity, we can get pretty accurate solutions. Here you get more viscous propagation, here you get more toughness propagation as the toughness increases. This enabled Jaeger to actually make the classic P3D model much more accurate. Here, in this case, when you've got a significant toughness, the classic P3D model ends up here, and by making the appropriate tip adjustments to the EP3D model with a non-local operator, Jaeger was able to come up with an EP3D model that's incredibly accurate. And so this is with 3 different multi-scale behaviors. I'm just going to run through these different animations, if you like. Symmetric stress drop, and you can see we're getting 3 different types of multi-scale behavior. You can extend this to multiple fractures. We've also looked at laminar to turbulent transition. Basically, you can introduce this adjustment to the viscosity, which captures turbulence, in fact. And you can see the difference between turbulent and laminar, less stress shadowing. And you can also take it to 3D. And I think that's pretty much all I wanted to say. So that'll leave a few minutes for questions, I guess.
Okay, thank you very much. It was a very interesting lecture. So now we are open for questions, please. Yes, Nikolai Nikolaevich, please, your question.
Thank you, Andrej. Thank you, Anthony. I enjoyed very much your lecture, but I have one small question. You see, when this assumption about the constant width, some W in the tip, there is the parameter L for the integration, and it can be chosen arbitrarily, or you have some recommendations, special recommendations, which I probably missed in your presentation.
So I'm just trying to, so let's just go back.
Yes.
Where was this?
Yes, here, I think, somewhere here or higher, yeah.
Okay, so
parameter
L.
L. Yes.
The parameter L. So basically, if you've given a trial width here, you know from the asymptote where the free boundary is.
Mhm.
Now you're using a fixed mesh. So we know where this boundary is. So all you need to do is to calculate that distance L. So we know where what the distance is from the left end of the element to the actual free boundary. Right? So that's what little L is.
So it depends on the mesh, I should say.
No, the mesh is here, but the mesh is fixed. But basically L will change as the solution updates, right?
Yes, I see, but just if the mesh is bigger, so about the position of, it is about the position of the cells. So
yeah, because I mean, if we look at this animation, here you determine the distance to the free boundary.
Okay.
And that is L there.
That means that it is time dependent, this L parameter is...
Well, you iterate on the front until it converges, that's it.
Yes, and that's why the tip thickness is also a time-dependent parameter, this W.
Yes, the W, yes, absolutely, yeah.
It's also time-dependent, okay,
yeah.
I see. And then if you permit one more very small question, when you showed your parallel fractures, plane fractures in 3D,
yes.
There were several, 4 I think, that it seems to me that they should diverge. So they should bend from one the other. This is due to their interaction, and I didn't see it here.
No, absolutely.
They were planar, absolutely. Because I expected that 2 fractures on the sides, they will not grow faster, but they will be bent.
Yeah, they'll be allergic to one another, right?
Yes.
I mean, there is an assumption here that the difference between the minimum confining stress is keeping them all in parallel planes.
Parallel plane. Okay,
so that's the underlying assumption. Indeed.
Thank you very much.
Indeed, if there was not that stress anisotropy, you would get the fractures will be allergic to one another. But that's a much more difficult thing to model, right? I'm working on that. That's the last set of slides where we were working on a triangular implementation so that we could go into modeling surfaces, right?
Yeah. Okay, thank you very much.
Sure.
Okay, so unfortunately we have no more time for questions. So thank you very much once again, Professor Peirce, for a very interesting presentation.